So for those who don't know me, haven't seen me speak before, I'm Brendan McAdams. I'm an engineer at TenGen. One of the big products we make is MongoDB. And I spend my day working on stuff around MongoDB. I do a lot of work with Scala. Before I joined TenGen, I created a driver for Mongo and Scala called Casbah, which I now maintain there. And I spent a lot of time early on getting a feel for more and more of using Scala. That was really how I learned Scala. And early in my career, that was it. That was all I had done in the career in Scala. And I've given a talk at Scala Days and a couple of other conferences, and on my experiences learning, what I learned about Scala, writing a driver. The big thing with Casbah is that rather than reinventing the wheel for the networking part of Mongo, there was a perfectly good Java driver that already supports the networking to Mongo. So I figured I'll focus on all the parts that make things look pretty in Scala and leave the networking there. But one of the things I did come up with is that there are different people out there. So there are asynchronous frameworks like BlueEyes, where having a blocking network driver becomes problematic. And so I started to play with, I was sort of excited at that point to start doing more and playing with writing a pure Scala version of the Mongo driver. And I started to build something called Hammersmith, which is stable now. A version of it shipped with Akka 2.0 to do Mongo durable mailboxes. It doesn't have all the features yet. But a bunch of different people have contributed to it. It's been a lot of fun to work on. I've been busy the last few months and haven't been able to work on it much, but I'm starting to work on it again. And so I learned a lot about doing asynchronous I/O from doing that. And I want to use that to guide this a little bit. And we're going to talk about why we might do asynchronous I/O and a couple of the lessons that I learned, things that were hard to do that are easy to do in synchronous programming, and there's sort of patterns or tricks that you can apply to doing this yourself. So we have a couple of goals here. We need to stop wasting resources and blocking I/O. And I'll talk about some of the reasons why I rather, maybe speciously, accuse you of wasting resources. Because in blocking I/O, we have a very set path for doing things. And if we have to deviate from that path to maybe wait for something to happen, we can't really do anything else with those resources that are going on. We want to try to achieve C10K. Now, I've heard people say recently that C10K is sort of a laughable number because that was the target 5 years ago. C10K is a sort of shorthand term that refers to the idea of scaling to handle 10,000 simultaneous clients. There's people who claim now that that number is too low. But that was a number that's thrown out there when you're talking about asynchronous programming. It's a target. It's something where 10,000 simultaneous clients in a synchronous networking layer might be a little bit tough. And profit. Because ultimately, at the end of the day, we're not, most of us who are going to jobs every day, and as much as we like playing with these tools, we have to produce something for them that shows our boss that there's a reason we hid for 3 months and rewrote the entire system to use Netty, and not just because we heard Netty was cool at a conference. And so I'm not just going to tell you Netty is cool. I have my issues with Netty as well, but it's better than doing Raw NIO. But what I am going to show you is that there is benefit to doing it. There are things that are up and down about Netty, but on a whole, you get a big performance gain. So what do I mean with this? We are talking about I/O. By which I mean input-output. Is anybody not familiar with what I meant by I/O? Do I have to go back and explain? Computers take things in, they spit things out. They do, mutate state and have side effects. It's just the way it is. We're going to focus on networking. Technically, a lot of these interfaces, you can use them with files or something else. Like the NIO stuff has file iterators. We're dealing with networks. Under the covers in many operating systems, a network device is really just a file descriptor. And in a lot of ways, you interact with the kernel. It doesn't care whether it's a network or a file or something else. So asynchronous is not the same as non-blocking, but they're often lumped together. Because asynchronous describes a way of computing on top of non-blocking I/O. I tend to think of these as a little mini stack. They're two concepts that fit together nicely. Asynchronous is a way of making non-blocking I/O work well for you. Because there are some versions of non-blocking I/O out there that don't have the asynchronous. The way that they are non-blocking is they throw an exception that says would block if they were going to block and expect you to do something another way. In the last few years, we've all gotten used to asynchronous being hand in hand because most frameworks have realized that throwing a it would block if you did this exception isn't very productive. So we have a couple of problems with blocking. When we have a blocking I/O operation, everything in that thread really halts and waits. So if I go do a big piece of computation, or I'm reading off of a disk. So imagine you're on EC2, which happens a lot these days. EBS volumes are a network device. And they're probably a disk that 5 or 6 other people have that spindle. And so you're waiting for that spindle to go to your devices. You're waiting for it to spool over the network. And while you're waiting for that read off the file system, that thread of execution is basically doing nothing. It's sitting there spinning, saying, are you ready yet? And that's really it. Internally, you've got a big loop that's saying, are we there yet? You know, if you remember being kids, the trips you didn't want to go on, you probably figured out early if you bugged your parents with, are we there yet? They'd threaten to turn around. You know, in some cases, that can be to your advantage. We don't want that with I/O because it's a waste of resources. And a lot of us have also gotten to the point where a lot of us aren't using physical hardware anymore. And it's easier in some ways to have this happen and ignore it because it's so easy to get another machine. But at the end of the month, I've had places, you hear the boss coming around asking why the EC2 bill is so absurdly large and how does he revoke your access to spin up new resources. And we need to deal with this. We need to handle this idea. So idleness is essentially happening because the thread is waiting for the I/O to complete, and it's doing nothing else at the time. So there's really no need for that thread to be sitting there doing nothing because the kernel is the one that's really handling the, is this I/O done yet or not? So this limits our ability to scale because we're just sitting there doing nothing. It's the equivalent of, I'm not screwing around, I'm waiting for my code to compile. So non-blocking I/O gives us potentially a solution, which is we can avoid blocking on each operation. We can find ways to work with the kernel to manage multiple blocking resources in groups. So we're still going to have to poll somewhere. But in most modern operating systems, there are a couple of things like select and epoll, KQ on FreeBSD, that understand that you don't want an event loop running for each operation you're doing, but instead you can ask the kernel of, you know what, you're the person who's ultimately deciding whether this resource is available or not. Would you be so kind as to just tell me when this group of files have something happen to them within a set of what I care about? So we can free up threads that are no longer blocked waiting. While they're doing the I/O, we can just do something else with that thread. We can execute some other callback or some other piece of code, and there's another event loop running that's telling us when whatever we're waiting for happens. And that's really how Node.js works. Node.js is a single event thread. There's no threading. It's just a big event loop. And it's firing off callbacks when something happens on a piece of information that's registered in the event loop is interesting. It's a single thread. We have the benefit of threading, which means if we're smart about it, we can make this happen at scale. We can use multiple cores and all these other things. So where asynchronous comes in is if we're no longer blocking and we're reusing our threads, we have to figure out how to handle completion events. And callbacks are a nice, easy way to do that. So async techniques, they give us that solution. It's really the equivalent of, you've been to different restaurants. I've seen different fast food restaurants where some of them, for whatever reason, you order your food and it's going to take them 5 minutes and they make you stand there and the cashier isn't serving anyone else while they're waiting. And then some give you a number and you step to the side and they call you when you're ready. That's really the asynchronous. I can serve 5 other customers. We've got people in the kitchen whose entire job is to cook the food. They will let us know when your order is ready and then we will call you, as opposed to me sitting there at the register waiting for your food to come up. It makes no sense. The synchronous and blocking I/O really forces us to do certain things that we may not want to do. And that's things like in a server, we're more or less at a 1-to-1 ratio of client connections to threads that we're running. It's worse if any of you dealt with the really Apache 1X and the pre-fork model in Apache 2 is the similar thing where it's individual processes. You had one parent that was responsible for accepting all connections and then queuing them until a child was available, and a child process could only handle one thing at a time. That's an exploded way of thinking of what's really happening. We're just doing it with threads. We're doing it with lightweight processes instead of actual processes. There's still overhead. There's a heap size that comes with all of these things. Threads have overhead. Despite the argument I got in an interview once with someone who thought you could spin up 1 million threads with no overhead, there is overhead to threads. On the client side, we can end up with a lot of other problems, and these come and go. Different people have different opinions. But you can end up with connection pools that are bigger than they need to be. Because while you're waiting on the server to respond to a request, or while you're waiting on a connection to be available for writing, you're sitting there blocking, which means you have to have more connections ready to go at any time because you've got this 1-to-1 ratio going on the server. In many cases, clients are something sitting in a server. In a web application, you'll probably have an asynchronous or a synchronous server with a client to a database or something else within it, which means both rules are going to apply. If we go asynchronous, we can change this up, though. With servers, we can have many client connections to one execution thread as a ratio. It can happen. It's possible. And this gives us the ability to scale up. We can have a thread waiting for an I/O response, not need to block on it, but give some other callback a chance to do work. An operation such as write can be queued up until something is ready. So we don't have to block until the write happens. Instead, we can say, look, I realize all the connections are not available right now, but I need you to write this to the database. And I'll call you back when it's ready to happen. You go do something else in the meantime. So basically, go to sleep and let somebody else use this thread. This, of course, means we have to know how to dispatch back to people. We have to good callback code. We have to figure out when a message comes back from the server that we're connected to, who the hell it goes to, and what callback to open up and run. We also have to understand concurrency. Because otherwise, you get all sorts of weird race conditions and fun things because you're sharing state across threads. One of the benefits is potentially you may not have the same thread that ran before run your callback. We also can't really block within those threads because this is a framework built around the idea of you're not blocking. Anytime you block, because we're trying to have many client connections to one thread, if you're blocking, you're slowing everyone down and you can't process as much anymore. And we can reduce our pool sizes on clients. And we can leverage these resources to reuse them. So a little bit about NIO. Most people have heard of it. I hadn't played with it much until this year. It's short for new I/O. It was actually introduced in Java 1.4. And really what it produced is a low-level I/O API instead of the old I/O, which is very high-level, blocking. It's sort of the socket interface. There's a couple of cool ideas in here that we just, within a 25-minute, 30-minute time window, we don't really have the time to dig in. This is an article I highly recommend. Apparently this guy works with Jamie Allen now at Chariot. But he wrote a great article on what byte buffers are, which are one of the better things introduced in NIO, which is this idea of it's zero copy holders for things like arrays and other data. So instead of you having to do system array copy, you can do things like slicing out a piece of a buffer of bytes, an array of bytes from a byte buffer, but it's still pointing to the same memory location as the original byte buffer and not copying them around. And this gives you a lot of efficiency. You even have the ability to allocate directly on a heap with no GC of these, although that tends to be dangerous and you have lots of memory leaks seem to occur with those. Because if you don't free them up properly, just like in C, you end up with memory leaks and odd behavior. So for working with a network, we have to manually work with a selector and request a window to read and write. That calls back when ready. And there's a couple of core units of work. We have a buffer, a channel, and a selector. The buffer are basically contiguous memory slots. They're able to hold information, whatever that information represents, and they typically offer some kind of a data transfer operation. Shift this to this other buffer, shift this to this file descriptor on disk, whatever you need to do. Channels are really bulk wrappers to this. They're there for us to do bulk operations like reading and writing to a file descriptor, be it a network, socket, whatever else. The big piece is this part where we have to figure out what's going on. And instead of us having to pull on a channel to see if it's available to read or available to write, we give information about each channel to a selector. And we write an event loop around that, which is monitoring for whether anything's available in the channel instance. So really, you register interest. I would like to read, I would like to write. And that loop will come back and give you information when it's ready. So you can maybe have 100 channels, but there's one thread which is handling the is things available and dispatching as things come up. So we can relocate the task of checking this I/O off. And it makes a big difference. And you can do all sorts of different tricks. There's a really good article that I don't have the link up from Havoc Pennington on his blog. I think it's blog.ometer.com. He did a great article a few weeks ago about this kind of thing and talks about even techniques for making sure that you use all the cores so that you're minimizing your threads so that you've got event loops maybe on each core and how this compares to stuff like Node. The reality is I've tried for 3 days to come up with NIO example code that isn't going to be a sinkhole. You've all seen these presentations where you show code really early on and everyone gets scared and you either take out your laptops and start doing something else or you just get up and leave. I don't want to do that. I think it's better to describe the concept of why NIO is difficult, show where Netty improves it, and talk about the conceptuals, than to try to show you a very complicated piece of code that's kind of insane. They went a little too low level with NIO, which is why things like Netty exist. So here's what you really need to know. I mentioned you register interest with a selector. I'm interested in reading, I'm interested in writing, whatever you need to do. But it's non-blocking, which means you have to basically give it a callback and say, let me know when you're ready to let me do what I want. We write a loop that looks for these notification events. And we have to dispatch incoming events. So if we want to read or whatever else. If you want to write, this is where it gets nasty, I think. You have to tell a selector that you're interested in writing. And eventually, when the channel isn't busy reading, it can switch into a write mode and call you back and say, hey, I've got some availability to write. You then need to make sure you remove the status that you're interested in writing, because otherwise you'll keep getting notified that it's available for writing. You need to dispatch a, hey, I'm ready to write call to whoever that callback is, and then you need to do your write. So it gets very complicated. It's also an area where you can very easily get into trouble if you miss a message or miss something. And rinse and repeat as desired. So obviously, the first thing that seems to have happened with NIO is everybody built frameworks around it. So there was Apache Mina or Mina, Netty grew out of that. You know, all of these things are meant to give you this functionality and this performance without all the complication. I tend to think Netty went a little overboard because it is a Java framework. So in Scala, I feel like I'm doing a little too much Java to work with it. But this really simplifies NIO. They actually also have a package called OIO, which is how they refer to the old IO. You can use blocking sockets within Netty if you need to, but the framework design is very oriented towards assuming you're doing async. So it's just really a wrapper, and it hides all the selector stuff away. You no longer have to say, are you available to write? Instead, what you really just say is, here's a buffer. This is what I'd like to write, and then it takes care of when writing is available. It puts it on the network for you, which makes more sense. Really, it's built around a filter pipeline. So there's a pattern in Netty that you can register on both the input and output side to have filters that can transform data, check data, validate data, and dispatch it where it needs to be as it goes through each end. And it's very nice and composable, although I'd love to have a better Scala API for it. They also have a system called channel buffers, which seem to be a little up and down. A lot of people have had issues with them. Part of the idea of channel buffers is to not rely on the byte buffers that NIO introduced, because people might still want to work with byte arrays or anything else. What they don't want to do in Netty is if you give them a byte array, to then be forced to system array copy that all the way through the pipeline. And so channel buffers take a lot of the concepts from byte buffers and let you use multiple things. Not just you're forced to start with a byte buffer if you don't want memory copying, and copy these things through. And so you can have multiple composite buffers and everything else. And we avoid memory copying. There is direct memory allocation from what I'm told. I've heard rumors and seen bug reports of lots of memory leakage, which seems to be what happens when you start playing with direct memory in the JVM. So here is, quickly, I mean, this is, of course, because we're linking in with Java. This is an example from Hammersmith of setting up in Netty. So really, because I'm not going to walk line by line through the code, but the general idea is we're setting up a pipeline. So really, we give it a thread kubel executor so that it has the ability to kick things around as it needs to. And we add in this message decoder, which we're going to talk about when we talk about the problems here. We connect. Most importantly, this is all we have to do to do writing in Netty once we have a channel. It's a big improvement over what the NIO equiv was. Would basically say, I'd like to write now. Let me know when I'm ready, and go through 5 or 6 steps. So stupid pet tricks. Very quickly, if you've never heard of a MacGuffin, Hitchcock was fond of them. It's the idea of a plot device to carry something through. So obviously, we're talking about a driver I've written because it's a good way at looking at what these things are. We're going to talk about a couple things in Hammersmith. Basically, decoding and dispatching inbound messages. So you may have 1,000 people reading from one socket, although that's probably a high ratio. So you have to figure out, of the 1,000 people, who was this message destined for? Does it matter? Is it a reply to another message they sent? And dispatched it adequately. I'm handling errors and exceptions across threads, etc. Follow-up operations that need a same connection context. And working with multi-state iterations. We're going to talk a little We're going to talk a little bit about iteratees, which is apparently a tongue twister. Hopefully in an easy way, is how do we handle database cursors? So the first problem I ran into is really packets aren't bytes. You know, in every networking program, we have defined some kind of application level API, which is how we think of the world. The kernel, Java, etc., doesn't understand or care. To them, it's just an array of bytes, which means it's also difficult when we're doing asynchronous reads because we just get bytes. And we need to figure out which parts of those bytes are relevant to us. So if I have, let's say, 100 clients using a connection, I have to figure out messages, if I get 1,000 messages, well, which of these goes to what person? Which of these are replies? Which of these are generic things? And we have to figure out where they go. So the challenge is separating them out and sending them to the right place. So it's really the law of Demeter. In NIO, you're sort of forced to deal with that in place of knowing just enough about what's happening to deal with it. So essentially, you've said, I'd like to read now, and you've got to break this out. It can get very complex. You're sort of trying not to go into the office fridge and eat someone else's lunch. So NIO leaves us on our own. Netty's pipeline actually makes that really easy, because with Netty pipeline instead, we register something that understands how to decode our protocol. It picks out the individual messages from the byte stream and then uses the rest of the pipeline to dispatch those as we need them, which is a much saner way of dealing with this. So this is an example of how we decode the Mongo messages, which is, among other things, it's a length field-based frame decoder, because Mongo messages have a very specific length. The first 4 bytes of a Mongo protocol message is what the length of the rest of the message is. And so Netty provides a basic context for handling that of now, by passing the arguments in the constructor of how big the message can be possibly total, what the offset of the length header is, and then where to start, because Netty by default assumes that your length does not include the length in the length. We include the length in the length, which is what the -4 is, which is actually saying Netty considers 0 to be after the length. And so we have to say, no, backtrack and read the whole thing together. And so now we actually get a byte stream that's in a exact message, as long as a well-formed Mongo message came over the wire. And we can break that down essentially into our class. And I have a series of classes that know how to then turn that message into some valid representation of a Mongo protocol. And so this is just stuffed into the pipeline, and everything that comes in to read from that socket, Netty will decode into a message. And then there's a lookup table that says, essentially, these are all looking for replies from the server. And each reply has the ID of the message that was sent. And there's a lookup table that says, if this ID should invoke this callback. And everything gets where it needs to be. And this was just the tail end of that. So really, the tail end, the part, my channel handler, which is the part of Netty that's responsible for responding to messages that come in, this is invoked after that pipeline. So that reply message decoder goes before message received. So instead of in message received, get message gives you an object. But in this case, unless something's really broken, it should already be a Mongo message, because it was either decoded or an exception was thrown and that packet was discarded. I can cast that as a Mongo message and then do a case statement, a match, to what kind of a message is it and how do I respond to it? And I didn't think you'd want to see like 1,200 lines of Scala cases. I can pull those up if you prefer. But the general idea is, this is a huge advantage of something like Netty, is you have to understand how to slice out the pieces of the message that you're looking for and send them to the right place and deal with that efficiently. And not accidentally overreading the first 6 bytes of the next message, which makes the next message impossible to read because you've sucked 6 bytes off the wire. So handling errors, we get really used to, I think, using throw and catch, try catch, etc., throwing exceptions. But we never know what thread we might be executing on. So that thread might be isolated from our main execution area. And so if an exception is thrown, it may just disappear. Or it may bubble up the stack and cause other unexpected errors. And so we need a way of passing information about problems. Scala obviously has either, and either has 2 possible states, left and right. It's really a monad, and it's representing failure and success. By convention, the left-hand side is typically representing an error, and the right-hand side is representing success in Scala. Node has a similar system. If you've ever written node.js, every callback method, typically by convention, gets both a failure and a success, and you test which one is defined. This is better because it's one composed thing that can be either or. It cannot be both at once. There's no real different way to handle this in Netty versus NIO. It's just a conceptual. Either is a great thing because you can compose a throwable or an exception. You don't have to throw it. You can wrap it in this thing that indicates success or failure and pass that up to your users. And there are implicit tricks for lazy people who want to write a success block. And I'm going to skip through these a little bit to make sure we cover the other ones, but I'm happy to come back to them afterwards. We have a little extra time, I think, at the end. But the general idea here is these are a bunch of structures that are used within this driver that ultimately, when you're writing a request future, and without meaning to, I ended up implementing futures And then I realized it was a future and renamed the class, and ultimately it's going to be using a.k.a. futures. But the general idea is you give it a body, and the body is supposed to have a left, which is, in this case it's, the way the class is. But essentially a body is supposed to be an either of throwable or a success condition. And a handler looks like this. So really we're expecting to get back an either of throwable anyref, and you deal with a result. You deal with a either by doing case right is success, left is failure. You could have a global event handler or something else that handles errors if you needed to. And if you wanted to ignore errors, which many people do, you can make an implicit that sort of pretends as if they don't specify the either, it just takes the success and you can globally dispatch your error. Another one that I ran into was same connection follow-ups. So a lot of databases have context. There's something that has to happen on the same connection as your write. You can get follow-up information. MySQL is last insert ID, where MySQL can auto-increment an ID, and you want to find out what that ID was. But that has to be called immediately after the write on the same connection as the write, or you don't get the right info. Mongo has something similar. If you want to control write concern, basically the consistency, if you want to get information about the success or failure, Mongo writes by default are asynchronous. You have to make another call. It has to be on the same connection immediately after the write. So how do you deal with that? In a synchronous framework, it's easy. You get a connection out of the pool, you hold on to it, don't let anyone else touch it. Problem solved. You know no one else has written to that connection. In async, it turned out that really the reason was ballot box stuffing is what I like to think of. We're reversing the issue of once it gets to the JVM, the network, the OS, they don't know it's anything but a bunch of bytes. But if you give it one buffer of bytes and say this has to go on the network, it will guarantee that that whole array gets on the network in order because it's important. So the trick is to just put both protocol messages together in one write operation. And the OS will make sure they get where they need to be, which means on the connection it will get a write and immediately a get last error or a last insert ID, and it's going to get where it needs to be. And there's an example of it here, which I'm happy to show to people afterwards if they're interested in. But the general idea is just, if you want to do the write, add that into the stream. Netty makes that easy. So the last one, and this is iteratees. Everybody hopefully has heard of iteratees a little bit. The name floats around quite a bit. Scala Z has them. Josh Surratt wrote a really good article on them recently. So in typical iteration, we're dealing with basically a dual state monad. And this is an iterator of A that has two calls. Those calls are hasNext, which returns a Boolean. Do you have more information? And there's a call called next, which says give me another piece. And so you expect to get an element, A being the type of whatever you're looking for. In a simple form, an iterator is just pre-populated with its buffer of items. All the possible items it can return are there when it's instantiated. If the buffer is not empty, hasNext is true, and next will return another element. If the buffer is empty, iteration halts because hasNext is false. Now, if you actually look at the Scala doc, it turns out that it specifically says the behavior when next is called when hasNext is false is undefined. There's no contract in Scala. Basically, calling next when hasNext is not defined is going to do weird, unexpected things. Thankfully, like the for each expressions and all that, use hasNext to determine if they're going to call next. So as long as your iterator is written correctly and doesn't say it has more when it doesn't, you're OK. In a simple database, or a simple construct working over a network, a query might just return everything that was the answer to the query. And we could instantiate an iterator of database row. This is nice and simple because really we can just construct a database row iterator. It's got everything it needs. It can iterate the same way. But of course, forcing a client to buffer 10,000, 20,000 results is questionable. Do you have enough memory on the client for the entire result set? If we have a lot of async clients, we could have a lot of memory. And a lot of databases, Mongo, MySQL, Oracle, SQL Server, have something called cursors, which is buffering. The server is using its memory to hold on to these things. So a cursor is going to be an initial batch of results. So maybe you'll get the first 200 results. And it will tell us that there's more on the server that you could get with a batch. So in Mongo, there's a call called get more. I mean, it's similar in every database. Get me more. And there's going to be additional batches. There's going to be more batches. You keep calling get more when you want more results. And once it's exhausted, there's nothing left. Try doing this without blocking, because I did, and it was painful. because we have 3 states now in our iteration. The typical solution in asynchronous drivers just has next Boolean. If the local buffer is non-empty, return, or if there's more results on the server. Next can just, if it's non-empty, return it. Otherwise, go to the server, and an intelligent driver might be intelligently prefetching what's going on there. Asynchronously, though, that block on get more will kill you. I tried a thread.sleep at one point early on. I'm like, oh, I'll figure this out later. I couldn't figure out why the reply to the get more was never coming in. It's because I was sleeping and blocking the thread that was responsible for reading off the socket the reply that I was waiting on. So we're reusing a small pool of threads we won't want to block. And there may have been heavy drinking involved afterwards. And then about halfway home on the train, I went, oh, I was blocking the thread that I was supposed to be reading from. So I talked to a couple people, including John DeGos and Josh Surratt, who had suggested iteratees. I read some Haskell white papers. I read some Scala Z code. My head hurt repeatedly. There may then be more drinking. So I wanted to point out that I may be completely wrong on what I explained on iteratees. This is my interpretation. The general idea is instead of blocking next, we want to introduce a higher order function. We pass a function that takes an argument of an iteration state and returns an iteration command based on that state. Our code is now async, and if the response to, not quite what I wanted. If the response to no more on client server has some is go get more, you don't have to block the I/O. Because you can pass a copy of your current method with the get more, and you'll be called back when there's more. And the method will return as if you went to sleep and came back awake. So very quickly, because we've got about 2 minutes, I think. I don't know how, is that accurate to the original time, or do we have a few minutes after? OK. So very quickly, looking at an example of this, I've got 2 traits, iteration state, iteration command. I've got an entry, which represents, here's a valid entry. This is a proper response to next. I had local entries. Here's an entry. Do something with it. Empty, which is my indicator of there's nothing left on the client, but there's more on the server. And end of file, which says that both sides are exhausted. There's nothing else for me to give to you. On the iteration command, done means I'm done. I don't want to do anything else with this cursor. Clean it up and shut down. Next says, OK, get me another item. And here's a copy of my function again, a function that expects to take an iteration state and return a command. And then next batch, which does the same thing. It takes the function. Next batch says, OK, go to the server, get the next batch, populate your local buffer, and keep iterating me as if there was local buffer. This is on the actual cursor what the next method looks like, which is that instead of the next method actually working on the network, it returns a bunch of possible iteration states, which are fed into your iteratee method. There's a helper function that I wrote on the object to just make it easier for you to have, you can define iterate, give it a copy of the cursor, give it your command, and it will wrap everything automatically. So it invokes next when it needs to. It invokes next batch. And this is an iteration of a cursor. And really, we're looking here. And I don't know if the guys on the other side of the room can see me because I've got a pillar in the way. But really here, if we get a state of entry, process it. If we get a state of empty, ask for the next batch. And if we get a state of end of file, just close it up. This is also testing that you can return different commands to states than you expected. So if there's more than 100 items, it just shuts it down. Finally, there is in JDK7, I found this on the train up yesterday, a new thing called either NIO2 or AIO, depending on who did the write-up. And it actually has something called asynchronous socket channels, which fixes some of the problems with NIO being too low level without being as insanely high level as Netty got. So what you get is instead something that maps really nicely to what maybe you might expect from Akka, which is you don't have to select and poll by hand. There's a read and a write method. They all take optional timeouts. And you have 2 ways that you can get a response back. You can give it a future, which most people who've worked with Scala have probably seen in one form or another. Future is just really a method that eventually will return a result. You have the option of blocking on it. Or you can do a completion handler. If you look at what a completion handler is, it has 2 methods on a completion handler. Success, which returns T, which is your success instance, and error, which returns the error that occurred. So if you can be smart about writing your implicit, you could really easily write an implicit that converts an either down to a completion handler. So it could map very nicely. It's unfortunately not really something you can run with. I would love to switch Hammersmith to it because it requires JDK7. And I don't think anyone would be like, oh yeah, I have this great async driver, but you can only run it on Java 7, which no one's really using yet. So it's an idea, but not quite there. I already did post the slides this morning, so if you're interested in digging through the code and all that, the code for Hammersmith is up there as well. And if I haven't confused everyone thoroughly, I'm happy to answer some questions. So the slides are up. I'll be here for the rest of the day. I'll actually be here Saturday and Sunday as well. So if you have questions or want to have me walk you through any of the stuff you didn't understand, feel free. And thank you very much.